So good afternoon to all. I am Dr. Umesh Kumar, Associate Professor, Department of Chemistry, Yeshwantu College, University of Delhi. First of all, I thank to organizer to giving the opportunity to present some of my work here. So today I am going to present the work that is the titled Exploration of Cost-Effective Earth Abundant Metals for Enhanced Electrocatalytic Oxygen Evaluation Reactions. So for the sake of introduction, you all know for our energy demand, we are most of the cases using the carbon-based fossil fuels, and it also has this limited resources, and the energy demand is increasing day by day. So by using these fossil fuels, also we have the greenhouse effect because increasing the greenhouse emissions that's severely affecting the environment as well as the human health. So we require the green energy, that is where for that we have to develop this sustainable, cost-effective, renewable and usable energy. And this is the very simplest way, that is the nowadays very popular, so water splitting reaction. So this water splitting reactions involves two half-cell redox reactions, cathodic hydrogen evaporation reaction, that is called the HER, then hydrogen plus and this two electrons system giving the hydrogen and hydrogen gas, and another is the anodic oxygen evaluation reactions, which is the OER, that is the multi-step reactions which require the full electron systems. So to achieve the oxygen evaluation reactions, it is slightly different because it required high power potentials, it has a sluggish kinetics, and as I told you, this is the 4 electron multi-step reactions. As you can see the mechanism here for both the details, many articles is already known. So in this case, for this to achieve the oxygen evaluation reactions, the thermodynamic potentials is required, high thermodynamic. Discussing about this, the oxygen evaluation reaction required is high potentials, because it has the sluggish kinetics for electron multi-step systems. Therefore, the mechanism you can see it here. So for electrocatalyst, we need these reactions. The electrocatalysts that electrocatalysts will reduce the overpotentials, remove the kinetic barriers, and the electrocatalyst will be the stable, cheap, and easily synthesized. So people are using the noble metal catalyst, and we all know that this noble metal catalyst has been very useful for this organocatalysis as well as the electrocatalysis purpose. But we all know this is a very costly, it has a high cost but low abundance, and this limits the practical implications of this noble metal catalyst. So now people are switching over the earth abundant metal catalyst. It is the useful for, and not only in India, everywhere people nowadays using the earth abundant metal as a electrocatalyst, like nickel, cobalt, irons, manganese, any other metals of the earth abundant metals. And you can see that here the literatures, many people are already giving this very good articles, the review articles for the nickel based, cobalt based, iron based materials for the electrocatalytic activity. This is very clear, the very recent articles that indicates that many people are working in the respective area. So our objective is here to synthesize the new metal complexes as the metal green framework using earth abundant metals and use them as electrocatalyst for the HER or OER reactions. Sometimes this is not up to the mark, so we have to generate from these complexes and from the derived materials like metal oxides, metal sulfides, metal phosphides, these type of kinds, and use them as electrocatalyst. Even though they have not worked, people are giving the supporting materials like the graphene oxide, carbon nanotubes, these type of materials, and then use them as a catalyst for the different type of reactions. So achieved these objectives, we are doing different type of project here. So some of the project I am going to just discuss here. So project 1, this is a very simplest reactions. We just this cobalt, taken that cobalt oxide acetate and this 3,5-luteins in the acetonitriles. We have given these compounds, this cobalt 2 acetate, to water molecules and to luteins, this complex one. And these molecules have been first time characterized by single crystal data in my lab. These molecules, like they're very simple, but it has the opportunity like 2 water molecules and 2 carboxylate moiety oxygens is available for the hydrogen bonding. So it will grow very, we have seen that this supramolecular structure. Then we have seen that these molecules extended with the OH hydrogen bondings with all different sides. So we have just grown in the 3-dimensional way, and see this is the very interesting, this porous materials, looks like these porous materials of this holes, and these porous materials have different type of pores, hexagonal pores is already, you are seeing this pores here. So with this the surface analysis, we have just calculated the pore size and then seen that this molecules is very porous in nature. So this complex has been used as an electrocatalyst for OER reactions and compared with this bench-of-mark catalyst iridium oxides. And we have seen that this catalyst has been, the TO value of these complexes is 2.55, nearly 2.5 times higher than this iridium, the benchmark catalyst iridium oxides. So this is the very interesting complexes. So we have calculated this project synthesis of, we have synthesized these novel coordinated complexes, acetate complexes. This structure has been characterized by single crystal data. And this complex 1 shows the excellent catalytic activity, OER activity, better than state-of-art iridium oxides catalyst, which may be due to this three-dimensional porous structures, as we have seen earlier. Rapid transport of ions, because it has the different type of, it is very porous materials, it has holes, different holes. And this is the highly stable cobalt active sites, because this is the molecules is very simple. And this higher electron density around the metal centers. This is the conditional flexibility due to this carboxylate ligands. So the further this, we have done this after photocatalytic, electrocatalytic, we have done this XPS, FTI, RADX analysis that confirm the retention of these complexes in the bulk amount, but formation also of this cobalt 2 plus, cobalt hydroxide and cobalt COH group as a HER catalyst. And this work has been published last year, just 2023. The next project, just I'm going to briefly discuss this here. We have synthesized these new ligands, and these ligands have been reacted with this nickel chloride, ammonium thiocyanates, given this complex, nickel complex. And this complex again reported the first time by the single phase X-ray data. And we have seen this hydrogen bonding network here, but this hydrogen bonding is not much excellent like previous compounds. So we have gone on this TGA analysis of these compounds. So we have seen that this after the end product is given the nickel sulfide nanoparticles. So we have synthesized from this compound, just we have an ingredient for syndicates as according to the TGA, and then got these nickel sulfide nanoparticles, and this has been characterized by study data. And we have seen that semi images is very good semi images, like this nickel sulfide, diamond type of nickel sulfide is here, but complex is a very now the nanoparticles type of materials. So after that, we have just given the support of these materials with this nickel complex as well as this nickel sulfide nanoparticles with the functionalized carbon nanotubes. And then we have synthesized this nickel complex with CNT materials as well as the nickel sulfide CNT materials. And all 4 materials like nickel complexes, nickel sulfide CNT, nickel complex with CNT have been analyzed for the electrocatalytic activity for OER reactions. These materials also characterized by this power data and semi images. and this electrocatalytic activity has been shown here, and found that this nickel sulfide CMT has the best performance among these odds, even compared with the iridium oxides. So these are some analysis we have done by Tufts of Institute. We have done that, and we have concluded this that we have synthesized and structurally characterized the light hydrogenate complex to design the new and efficient OER catalyst. This nickel complex was used as a single source precursor to synthesize nickel sulfide directly by just simple annealing methods. Nickel complex and derived nickel sulfide coupled with functionalized carbon nanotubes to enhance the electrical conductivity and surface area. The performance of nickel catalyst as compared to the state of art iridium oxides is shown that this nickel sulfide CMT has been the best performer among these all. After that, this nickel complex CMT, then iridium oxides, then nickel sulfide, then simple nickel complex. So, on the last, we want to acknowledge this our Yeshwanthpur College, University of Delhi, and IIT Delhi. This SERB for this financial assistance. These two students is working here, and the Professor Parveen Ngole is helping us for the electrocatalytic activity. IIT Delhi.
Professor V. Krishna, the Department of Chemistry, the head of the Department of, I'm working in the Nadimpalli Satyanarayana Raju Institute of Technology in Visakhapatnam, Andhra Pradesh, India. That my entitled paper entitled Synthesis and Characterization.
Hello.
Sir, wait.
Yes.
Okay, sir. Synthesis and characterization and biological activity studies. Hello, sir. Are you audible?
Yes, sir. You are audible.
Okay. Synthesis and characterization and biological activity studies of a novel series of isomeric pyridyl-tetrazole ligand and bivalent metal complexes. They outlined the basic outline, the my PPT, the introduction, methods, results, and discussion and conclusions. So the introduction of that introduction, the first point is the biological activity. Isomeric pyridyl-tetrazole derivatives have been under great investigation as a part of an inorganic chemistry. The main role in the next one is the pyrazole rings are versatile ligands for the coordinate transition metals. Therefore, the synthesis of transition metal complex and contain the pyrazole rings, particularly tetrazole, their derivatives, and given the enormous significance due to their practical application. There is an increasing interest of tetrazole derivatives for the development of click chemistry. The recently Nobel laureates in that 2022, the click chemistry is a one part of this application. Another one is the tetrazole derivative. We have found application in therapeutic as antithyropeutins agent, antibiotics, and drug delivery for that AIDS treatment. The synthesis of DNA binding and DNA cleavage, cytotoxic activity of copper-2 complex, which are obtained by the reaction pyridyl-tetrazole derivative, which is containing the pentadentate arms likely ethyl and dimethylamine. The main root of the methods, the first scheme, cyanopyridine to form a tetrazole pyridine ligand. So the various ligands are prepared in this synthetic route of laboratory, 4 ligands. Conditions during the 10 hours, adding of sodium azoide and lithium chloride and DMF and reflection of the solvent, and in presence of catalyst of potassium carbonate, reflects 24 hours acetonitrile to convert that different derivatives of this pyridyl tetryl ligand. The second route of the scheme, synthesis of 1 nitrogen and 2 nitrogen substitute of copper tetrazole ligands, copper complexes. The physical parameters of that confirm the complexes, coordinate complex confirmed by ICP-MS analysis, elemental analysis, the carbon and nitrogen, oxygen. The copper confirmed by ICP analysis. The magnetic behavior by EPR study. The first complex 1.82, 1.88, 1.94, the 4 complex 1.96. The various melting point by the thermal analysis, the various melting points. Next, the electronic spectral data by using UV visible spectroscopy. The complexes, various complexes with combination of ligands, metal ligand charge transfer appears observed at 27,428. The DD transition 1633. The more effect in the third complexes because of the chelating effect in the 16,585. The IR bands by using FTIR, Semaj FTIR, confirmation of IR bands.
Actually, sir, your slides are not changing.
Not changing, sir.
Yes, now we got table 3.
Table 3. Okay. Sir.
Yeah.
It's okay, sir. Is it okay, sir?
Yes, sir. You continue.
Yes. Okay. The OH bands of one ligand, the 3 and 4th ligand. Ligand 3055 appeared in OH appeared. C double bond appeared for 1620, 1626 and 59 various affect the ligand. C double bond C ethane 1523 and 1400, 1518. The pyridyl metal pyridyl 14, 14, 15, 15, 4, 13, 44, 44 various types of ligand complex. And another one, the table 4 is the EPR study spectral assignment for the complex 1 and 3 at room temperature. One complex and third complexes. One is the alcohol, another one is NN dimethyl, amine complexes. The G parallel total gyroscopic value 2.62 and 3.30. But another one is confirmation of the DNA studies by various complexes in the third complexes, observation spectra, absence of in the presence of increasing the concentration of ctDNA, bottom spectra recorded by DNA above the spectra addition of 10 micro per liter DNA each time. Every time I have 10 changes, the observation is also increases. The next one is the effect of ctDNA on the observation of binding constant of copper complexes. The 4 complexes, the free band of 438 observations are appeared of lambda maximum value. The delta hyperchromic shift and botochromic shift. The third complex, the first complex is more botochromic shift in shift n to pi to pi star. The observation next to the kinetic study of the effect of copper to complex and viscosity of DNA, relative specific viscosity and versus of the complexes. The third complex is more effect flow of velocity. And selected the plasmid PB322 DNA cleavage study of the copper complexes at the concentration of 17 molar micromolar. The reaction various conditions, complexes in presence of hydrogen peroxide catalyst. The form 1, form 2, form 3, the percentage of complexes because of the chelating effect, there is no any effect that ctDNA. This is the main slide images of agrogel cells showing the result of electrophoresis method, plasmid of DNA, different concentrations, controls of LAN 1, LAN 2, LAN 5.
Sir, your PPT is not changing.
How, sir? Is it work okay?
Yes.
Yes, sir. The
Yes,
form 1 DNA, the control of because of that complex chelating effect, the DNA mutations will be controlled, and the other one is that selected of plasmid 322 DNA cleavage of tidy copper complexes to control the complex compared to remaining 3 complexes, more control of the third complexes. Next one, the cytotoxicity of the taxophene, the for ABC image and DEF and GHI at various in the duration of period of 12, 24 hours and 40 hours, more control that in that cytotoxic effect on the third complex. This is cytotoxicity of the observation of the study, different concentration level, duration of 24 hours. The human cell 7, the more effect that in the third complexes. So finally, the conclusion of that these studies, The Pyridyl-Tetrazole ligand pentated arming of OH and dimethylamine mononuclear copper-2 complex of novel biodentate ligand have been synthesized and characterized. Physiochemical spectral studies reveal that mononuclear complex distort the square planar geometry confirmed by the single crystal XRD. The confirmation suggested the structure. All copper complexes are with binder ctDNA. Complex 1 and 3 show higher binding constant, maybe due to the more symmetric nature in presence of H2O2. In presence of hydrogen peroxide copper complex, cleavage the DNA is more effectively, which may be due to the reaction of hydroxyl radical with DNA. All the complexes are cleavage DNA via oxidative path. The final point is all copper complexes are tested for the anti-cancer studies. The human cells line, the highlighted of the present investigation of the mononuclear complex are synthesized, pyridyl tetraligand, pendant ligand. The different regions, symmetric nature of present complex, attractive future to develop the chemotherapeutic drug. DNA binding and cleavage activity of the complex are investigated to confirmation of the ligand. The final last point is binding constant value show these complexes are evade binder and cleavage DNA through hydroxyl radical generation. Anti-cancer activity of present complexes is good. Encouraged to design the better and efficient the metal-based drugs. Thank you, sir.
Good afternoon to one and all. I am Vignesh Kumar.
Vignesh, can you please switch on your camera?
Sir?
Can you switch on your camera? Is it possible?
Okay. Okay, so just a minute. So, okay.
Yes.
Good afternoon to one and all. Good afternoon to one and all. I'm Vignesh, Scholar, Department of Bivalent. I'm going to present my topic of Valorisation of sand hydrochlone.
Vignesh, can you check network connectivity? Hello, Vignesh? Can you check your network connectivity? Voice is breaking.
Just
please check your connectivity.
so it's audible.
Yes, yes, it's audible. Please continue.
Flowable for sustainable construction practice. The letters of Dr. Ross, Associate Professor, Department of Engineering. Today,
Vignesh, your voice is still breaking. It's not audible. It's still breaking.
So now, what about now?
And now it's okay.
It's okay.
Yes, it's okay.
Okay, so in civil engineering, the structural damage is a major issue. Here, the structural damages occur due to the improper designing, improper maintenance, like that. Now, today I'm focusing the general backfilling effects. Generally, it's a global fill or control low strength material. It's a Portland cement, the mixture of Portland cement and cementitious material, fly ash, and this moment of water. It's got a very good characteristics of self-leveling and self-compacting. And it's a two types of flowable fills are available. One is excavatable and another one is unexcavatable. The both are having a characteristics of 200. They need of 200 flowability For excavable conditions, we need of a 0.7 megapascal strength. For unexcavatable conditions, we need a strength of 8.1 megapascal. Then it's a benefit of realism. It's readily available, easy to place in anywhere. It's a very durable, and we need a controlled strength and no need of inspection. The very low equipments we are using for here. Then it's a placed in all weather conditions. Another one very important advantage is industrial wastes are maximum level used in our CLSMs. It's applications of realism is quarry hydrocyclone waste fine material. It's removed from the manufacturing process of quarry products like as a fine aggregate and coarse aggregate. We are removing these fine particles. It's reduce the workability and the strength of the concrete. That's why it's removed and damped in huge level and damped in every quarries. This waste, sir, nearly 620 million tons of 620 million tons are dumped in every quarries.
Vignesh, am I audible to you?
Yes, sir. Yes.
Yes, sorry to interrupt you. Actually, your slides are not moving. It is still in third slide.
Okay, sir. Just a minute, sir.
Yes, yes.
So my objective to sir now. Sir, no, okay.
Now it's okay.
Okay, sir. My objective of my research is to characterize the EMS and slurry waste as access their suitability and design mix proportion to the used as a control low strength material and evaluate the performance by fresh and hardened properties. By here, fresh property is flowability and hardened properties. We are using the unconfined compressive strength. It's a major important property for CLSM. We are checking this property for different geotechnical applications. The physical and chemical properties of M sand slurry, it's compared to the river sand. Its specific gravity is 2.11 and the finest modulus is 3.8. Maximum dry density is 1.52. Optimum moisture content is 17.6. It's a higher value compared with the river sand. And the chemical composition, it's identified by the XRF testers as it's got a higher silica content and 18% of alumina and 10% of iron content. And another one important property it's got is a calcium content. It's important for binding. It's have 8% available in our MSS. It's a mixed proportion. We are replacing the fly ash into the our industrial waste. 15, 20, 25% and 30% we are replacing. The fresh density of the materials come under 200 to 2000 to 200 kg per meter cube. We are focusing in here in two properties. One is a flowability and another one is a unconfined compressive strength. In flowability, we need a flowability of 200 mm for self-leveling purpose. Here we our material reach at 55% of water content to 200 mm flowability. For a P sand, plastic sand and manufacturing sand based CLSM reached at 21%. And our mixers reach only in a 51 to 55% because of this specific surface area of our material is very high compared with our normal manufacturing sand and plastic sand. And it's have a lot of porous content is high in our MSS. That's why it's absorbing a lot of water. It's reducing a bleeding. Bleeding is nothing but it's unreacted water in cement. It's come out as a bleeding water. It's as a bleeding. It's as per ACA conditions. It's not more than 5%. Our material come under 1.4 to 1.7% only. And then we are moving to the hardened properties. Hardened property we need of 0.7 megapascal. All the mixes are reached at 0.7 megapascal. We are choosing an optimized mix based on the various parameters, MSSFA, probability properties, structural properties too. We will optimize it. MSSFA 25 is optimized to implementing into the field. It's our field implementation. It's implementing in pilot scale level only. We are excavated in a small area, 1.5 meter into 1.6 meter area, and we are placing in our CLSM and performance analysis done by non-destructive testings. We are using the rebound hammer test and ultrasonic pulse velocity test. We are done for this identification of performance. Ultrasonic rebound hammer test, we are our value of hardness come under the range of 17 to 23%. It's a very lower value compared with the normal conventional concrete, but this our CLSM only replacing for soil only. That's it's a sufficient strength. Like as UPV, ultrasonic pulse velocity test, it's a range from 0.11 to 0.26 kilometer per second. Here we need a strength of 3 and above for a normal concrete. It's also too low value compared with concrete. It's okay for, but it's okay for soil replacement. It's a conclusion. Based on the serious experiments were conducted, optimized our mix. It's appropriately meet our requirements, and our mix come under the range of excavatable conditions. And the results for all the mixes come under 0.5 to 1.2 megapascal and satisfy the flowability of 200 mm. And our non-destructive test results also satisfying the strength performance. These are my some reference. Thank you.
Good evening, everyone. Myself, Dr. Vikas Kashyap from the Department of Physics, Punjab University, Chandigarh. The topic of my research that here I'm to present is structural analysis of silver nanoparticle deposited on silicon wafer and their influence on silicon nanowire-based gas sensors. The outline of talk these are the topics. So from the general background, the nanoparticle depositions refers to the process of attaching nanoparticles to solid surfaces called substrate to create coating of nanoparticles. The coating can have a monolayer or a multi-layer or organized or unorganized structure based on the coating method used. Nano-size film can also be produced by the top-down approaches such as the lithography or etching, where larger materials are broken down to create nano-size structures. However, there are limits to how these top-down approaches can go to the bottom-up methods are required to realize extremely thin films. This is a kind of nano-size film which is showing on the right side of the screen. The most common bottom-up deposition method for fabricating nanofilms are chemical vapor deposition, physical vapor deposition, and atomic layer depositions. We have deposited silver nanoparticles. From that Ag nanoparticles were deposited on the silicon 1,1 is the face of the wafer, where the dimensions are given by 2 cross 2 centimeter square. Resistivity is the wafer resistivity is 0.001 to 5 ohm centimeter through a cost-effective chemical method. To deposit Ag nanoparticles, the clean wafer were dipped in a solution containing 4.8 molar hydrofluoric acid and 5 millimolar silver nitrate for different deposition time 3, 6, and 9 minutes at room temperature. The optimized growth of Ag nanoparticle was found for the deposition of 9 minutes, and the schematic diagram of the deposition of Ag nanoparticles by the chemical method has been shown in the figure, where the clean silicon wafer that is cleaned by the ethanol and isopropyl alcohol by the ultrasonification we have done. By the dipping in the deposition solution, that is a combination of the chemicals which is silver nitrate and hydrofluoric acid and deionized water. After that, for that 3, 6, and 9 minutes, we have kept the silicon wafer in that solution. And the 9-minute was that optimized time where we find out the Ag nanoparticles whose FSM image is shown on the last of this and last of the panel. And the deposition of Ag nanoparticles is showing here in the figure, that is N40 and P40. These are the sample name, and on the N40 that is the N type of silicon wafer, and that is the P type of the silicon wafer, where that diameter is 81 nanometer in that N type, and the diameter is approximately 96 nanometer, which is calculated by the image software. The deposition of the Ag nanoparticles, which reveal the spherical, uniform, and homogeneous and crack-free growth of the Ag nanoparticles. The elemental mapping of Ag nanoparticles shows the presence of 91% silver, 7% of oxides, and 2% of the carbon. The elemental spectroscopy, diffuse spectroscopy spectrum reveals strong signal in the Ag region and confirms the formation of Ag nanoparticle with an estimated average size, which is around 47.3 nanometer onto silicon wafer. From the previous studies, it was Ag nanoparticles generally show typical optical absorption peak approximately at 3 kilo electron volt due to the surface plasmon resonances. The surface area of the Ag nanoparticles has been calculated through the Brownian-Emmett-Teller-Bet, that is the main technique. The theoretical particle size has been calculated from the surface area using the equation. From this process, we are going to the next step, which is that formation of the silicon nanowire. In the formation of silicon nanowire, firstly, we have to deposit Ag nanoparticles on the silicon wafer. After the deposition process, there is a second process which is known as the etching process, which we continued after that deposition. So, what the need of the silicon nanowire now in the nanotechnological industry, or the new nano era, that is saving the energy in the waveless form, high stability and non-toxicity, high carrier mobility, high mechanical strength, thermal stability, high catalytic activity, electrical conductivity, imaging magnetic and optical properties, application in the field effect transistors, as well as manufacturing efficient batteries and solar cell sensors. The right side of that presentation, that is the images, FSM images of the silicon nanowires, and these are fabricated by us. And and the synthesis of silicon nanowires as till up to now, the fabrication is taken by that electron beam induced deposition, that is a top-down approach, VLS method, vapor liquid solid method, while the bottom-up approach, epitaxial growth, chemical vapor deposition, that is a bottom-up approach as well. And lastly is a metal-assisted chemical etching, which is a MACE method. This is the simplest and cheapest method for the synthesis of semiconductor nanostructures. All procedures are accomplished in the chemical lab without expensive equipments. It is much more flexible and can be used to make higher surface to volume ratio structures. Crystalline quality of silicon nanowire is generally high. There is no obvious limitation on the size of feature fabricated by the metal-assisted chemical etching. The method has been utilized to fabricate various silicon nanowire or silicon nanostructure. This is the experimental kit which we have used. This is a very cheap method where the only one or two equipments we need, that is like pipettes and diamond cutter as well. That small bottles are showing, which is the cap of that our tonic bottles, which we have taken from the medical shops. And this is the schematic diagram of the formation of the silicon wafer. Where silicon wafer, after the deposition process, then again deposition of Ag nanoparticles, we have cleared in the next slide also. And the last, when we have Ag nanoparticles only left there, because after the etching process, only Ag nanoparticles left, we will remove that stray of Ag nanoparticles through treating them with nitric acid, that is HNO3. From the FSM studies, as pore propagate through intermediary silicon channel, the etching process result in the interconnected pore connections of cheese-like structure, as seen in this figure A. Here, these all depend upon the deposition of Ag nanoparticle on the silicon wafer. As we have increased the deposition time, then cluster of the wire form, which is like this is as the figure 3A is showing. It reveals that the length of the deposition silicon nanowire increases due to enough oxidizing species present in the solution to oxidize silicon. Figure last one is the reveals the dense of the silicon nanowire have been successfully fabricated by using the MACE technique. The silicon nanowire have been clubbed to form the porous structure on the silicon wafer, as shown in this figure. The schematic diagram is also here shown below, because in the last slide, maybe that proper diagram is there, that how these silver nanoparticles are deposited on the silicon wafer. After that, only silicon nanowire is left, and only residual Ag nanoparticles are left there, which we treated at the last by the nitric acid, and we removed the Ag nanoparticles, and we only left with the silicon nanowires. This is the XRD pattern. The XRD pattern showing that the 80 degree of Ag nanoparticle sample, that is Also, the estimated value of the lattice constant for various lattice plane and error functions. Figure 4b shows the spectra in between f theta along x-axis and lattice constant A along y-axis corresponding to each plane of the nanoparticle. By extrapolating the error function to 0, the corrected value of lattice constant has been found. The value of NCS, that is a nanocrystalline size, and lattice strain of a nanoparticle can be directly determined by the plotting 4 sin theta. This is a famous method. These are NR is Nelson relay plots, and modified Scherer method also used. From that, we have a comparative study we have done. And the method from these different models which are given, we calculated the NCS and the strain value by putting into the formula, that is a nanocrystalline size and the strain. The value of the NCS can be directly determined by plotting beta d along log 1 cos theta as shown in the figure 4c, which is the previously shown, which gives you usually a linear region. Further, the value of the NCS can be calculated by using intercepts. This is a modified Scherer formula. The lattice parameter is given by lambda by 2 sin theta under root of h square plus k square. This is a given formula as well. All reflection plane correspond to a nanoparticle with the FCC crystals. The interplanar spacing between the planes, lattice constant, and atomic volume corresponding to all reflection planes 200, 220, and 311 are summarized in the table 2. As well, average lattice constant obtained from experimental data is around 0.408 nanometer, while estimated lattice constant from Nelson relay plot is 0.407 nanometer. The wave equation is a straight line equation and is known by the modified Scherer equation. The FWHM, that is a full breadth and half maximum, NCS, microstrain, and dislocation. These are all the microstructural parameters using the simple Scherer model. Average lattice constant obtained from the experimental data is around 0.408 nanometer. The above equation is a straight line, which is given by the modified Scherer equation. According to Scherer formula, average NCS and microstrain for Ag nanoparticle present in the sample are expressed in this equation, that is a k lambda by beta cos theta. This is the famous formula as well. I hope so everybody knows this. Here, beta d and k represent the full weight and half maximum due to the NCS and shape factor respectively. The estimated value of NCS of Ag nanoparticle using Scherer formula and microstrain corresponding to Ag11, Ag20, this is the phases for sample with deposition time of 9 minutes. So the values of that FWHM and NCS are given in the right of this slide. The next is the sensing. We have done that sensing behavior. We have checked out by acetone gas. We have put on that silicon nanowires. The design is as already told that the area of that wafer is 2 cross 2 centimeter scale. The array was pre-cleaned and deionized water, ethanol, and isopropyl alcohol for the timing of 50 minutes of each by the use of ultrasonation technique as well. So silicon nanowires, we have contacts we are made by the silver paste and the lower of that silicon. And after that, there is a silver nanoparticles which are deposited on that silicon nanowire, which is shown in the slide C as well. And after that, the acetone, when we use that acetone as a gas, the silver nanoparticles which are stuck into that silicon nanowire as well. And we are finding it by the using the LCR meter. The working mechanism of Ag silicon nanowires, it is a heterojunction made by the silver and silicon nanowires based gas sensor, which is the schematic diagram of acetone sensing illustrated in this figure, which is demonstrated that silver serves as an oxygen diffusion catalyst, due to which adsorbed oxygen can diffuse fast to surface defect on silicon nanowires associated with the capturing the free electron and constructing O2 negative ions at room temperature. Additionally, the embedded Ag nanoparticles over silicon nanowire act as Schottky contact, which leads to produce much stronger depletion laser in this heterojunction as shown in the figure A. When the gas sensor is exposed with acetone gas, which had been depicted in the figure B, that acetone molecule react with the oxygen ion on the surface of silicon nanowire with the assistance of silver as a catalyst. The reaction of the chamber is given below. The rate of the reaction between the oxygen ion and acetone molecule is greatly accelerated by the Ag catalytic activity, and these reactions can take place with varying temperatures. The reaction between O2 negative and hydrogen, that is the adsorption process. We know that absorption and adsorption are both have the different meaning as well, can release free electron flowing back into the conduction band of silicon nanowires, which result in an increase of carrier density and a decrease of the depletion lesion. Same. When the charge carrier density of Ag nanoparticles are in the exposure of acetone gas, the gas sensitivity has been calculated by the equation, which is given by where S is the sensitivity target gas, delta R is change in resistance, and Ra and Rg is the resistance of air and target gas respectively. The gas sensing behavior of AG nanoparticles based gas sensing device has been depicted in this figure, which is based upon the chemi-resistant mechanism for sensing the acetone gas. The variation of resistance with varying frequency at different gas concentration of acetone gas has been portrayed in this figure. Gas sensing of AG and silicon nanowires, resistance with varying frequency at different ppm, that is a gas which we are providing for that sensitivity and the frequency, showing the graph in the figure B. That with varying frequency at different temperature and sensitivity at specific frequency with varying temperature. From this, as the frequency increases from 1 kilohertz to 5 megahertz, the resistance of this introjection decreases rapidly till when 1 megahertz, then slow down till 3 megahertz and become almost constant over 3 megahertz to 5 megahertz, which is due to the saturation polarization occurred in the material at higher frequencies. With increasing acetone gas concentration from 10 ppm to 200 ppm, the resistance of the devices is slightly increased and found maximum increment at 200 ppm, which is due to the more concentration of target gas available in working atmospheres. Figure exhibit the gas sensitivity. This is a second one figure with varying gas sensitivity with the varying at different acetone gas concentrations, which shows that as the concentration of the acetone gas is increasing in chamber of the acetone molecule, react with absorb oxygen ion available on the surface of AG and silicon nanowires based junction. The rapid reaction is possible because of silver acts as a catalyst, gets and create free electron, which is responsible to decrease its resistance and hence sensitivity increases. The detection of the acetone gas at frequency 1 megahertz is maximum for all the gas concentration, and the maximum response has been achieved for 200 ppm at same frequency that has been shown in the figure C. As frequency increases from 1 megahertz to 5 megahertz, the gas sensitivity towards acetone gas decreases due to the drastic change in the resistance of device in resistance in acetone gas atmosphere. The variation of gas sensitivity with temperature at maximum concentration has been reported. The sensitivity of the device toward acetone gas is maximized at 50 degrees Celsius and at higher frequency, that is of 5 megahertz, which gives the information of the AG nanoparticle silicon nanowire-based gas sensor is suitable for the detection of acetone at lower to higher frequency with higher detection rate. The maximum sensitivity at operating temperature of 50 degrees Celsius is remarkable result of this research. From this, the conclusion of my talk is that in this study, we have successfully deposited uniform AG nanoparticles on silicon 11 using simple and low-cost chemical method. We have studied FSM and XRD analysis for morphological, elastic, and microstructural behavior such as phase identification, peak broadening, NCS microstain, stress, energy density of AG nanoparticles. In resemblance to standard XRD analysis, we have utilized practical models to estimate the value of various microstructural and elastical parameters up to the reasonable accuracy. The NCS has been calculated through modified Scherrer model, which provide better accuracy than the Scherrer model. On the other hand, we successfully deconvoluted the X-ray line broadening due to the NCS, that is a nanocrystalline size, and microstain using the modified WH, that Williamson-Hall method using UDM. The NCS predicted by SS plot model and HW model are found to be in close match. The similar trend is also shown by the Scherrer and modified Scherrer method as well. As we can make silicon nanowire from these different size AG nanoparticle, as that help in synthesizing AG and silicon nanowires by metal-assisted chemical etching. The role of AG nanoparticles is as a catalyst in this heterojunction of AG and silicon nanowires sensing material, which enhance efficiency to detect acetone gas at minute concentration. The acetone gas response of this heterojunction based gas sensor at operating temperature of 50 degrees Celsius is found to be 98.8%, which is indicated that this is a prominent material for fabrication of acetone gas sensor, which has the capability to detect the presence of acetone in environment at very low concentration, that is at very low ppm.